Assalamu alaikum. So today we will discuss some problems related to two or many particle system. Okay, in advanced quantum physics. So the problem number one, what it says: find the expectation value of two distinguishable particles. So you just have to find the expectation value for two distinguishable particles. Okay, so if two particles are distinguishable, what it means, their wave function must be different, both of have. So let's suppose the particle psi, which has x1 and x2 position, and this wave function must be distinguishable, so that's why it becomes equals to psi a for particle number 1 and psi b for particle 2. Okay, and x1 and x2 are their positions respectively. So if you want to find expectation value, so you have to take the mod of that wave function multiplies with the expectation value. If you want to find the expectation value with respect to x1, so you will take x1. Next step, when you are finding the expectation value with respect to x2, you will multiply your psi mod with x2, mod square with x2. Okay, so here just you have to take the psi mod square. So psi mod square becomes equals to psi conjugate and psi. Okay, in between, because we are finding expectation value, we will taking x1 for x1. Now you know the value of psi here, psi a x1, psi b x2. You have to take their conjugate. So what goes, psi a conjugate x1, psi b conjugate x2. This becomes this x1 as is this. Next you have to put the value of psi x1 and x2, which is the same. You have to write this because there are two position dependents, x1 and x2, so you have to integrate along with x1 and x2. Okay, both. So here you will use double integration. Okay, not single integration. One more integration from minus infinity to positive infinity. Okay, so after this, what you are going to concise is that you are going to concise your x1's position on one side and x2 positions on other side. You are finding with respect to x1, so here is x1, here is x1, and here is x1. Combine these all x1's parameters, multiplies by another integration and x2 parameter and x2 parameter and x2. Combine these, you will get this. The conjugate of wave function along with that wave function, this is orthonormal condition, and orthonormal condition must be equals to 1. So this parameter becomes equals to 1. And what is this? This is the expectation value. You see, this is simple wave function, this is the conjugate of that mod function, and in between x1. So this is basically becomes equals to expectation value of x1, because along with a particle, so that's why a particle. Similarly, if you are going to find the expectation value with respect to x2, you will take x2 in between. Okay, your psi of x1 x2 and psi mod square. Okay, again you have to combine the x1 parameters one side and x2 parameters to the other side. So here x2, here x2 and x2. Combine these all x2 parameters and x1 and x1 and x1. Again this. Again you see wave function along with their conjugate must be orthonormal condition, and this is equals to 1. And this is, you see, wave function, their conjugate, and in between there is x square. So this is the expectation value of x2, because now this is for particle B, so this becomes equals to B. So this is how you have to find the expectation value of two indistinguishable particles. What if it says find the expectation value of three distinguishable particles? You just have to take one more wave function c along with x cube, and you have to integrate dx1, dx2 and dx3. You have to take triple integration. Understood? Okay. Now move towards next problem. Two particles wave function of boson. You have to take two particle system in case of bosons, and you have to normalize and you have to find the normalized constant A in case of bosons. So because these are bosons, so these are indistinguishable particles. Now these are not distinguishable, these are now indistinguishable particles. What you have to take, as we know, two particles wave function of bosons are can be written as, for indistinguishable particles, you can know that psi x1 x2 becomes equals to psi a x1 psi b x2, again psi b x1 psi a x2, in between plus, because these are bosons. If these are fermions, you have to take minus here, keep in mind, and that is the A, which is the normalized constant. You have to find this A, the value of this A. Okay, so you just have to normalize. How to normalize? You have to use the formula of normalization. You know what is the normalization? Integration along minus infinity to positive infinity and psi mod square. Because psi dependent is for two particles x1 and x2, two positions, so you have to integrate our two positions, dx1 and dx2. Understood? Okay, so you have to take mod square. What is mod square? Mod square is basically the multiplication of psi with their conjugate. So this is the value of psi as it is, I write, of two particle system of bosons, and this is their mod square. This is their conjugate. Psi A equals to psi A star, psi B and psi B star, psi B star, psi A star. Conjugate of this expression. Multiplication of conjugate with simple wave function. This is basically normalization. Okay, and A from here and A from here. A multiplies by A becomes equals to A square, and A is the constant, not depend upon dx1 and dx2. So these A square becomes come out from the integration. Alright. Okay, next you just have to use multiplication, simple mathematics. Okay, this multiplies by this multiplies by this, and this multiplies by this multiplies by this. Understood? You see, so psi A star, psi A multiplied by psi A star, this is becomes equals to psi A mod square, and psi B star multiplies by psi B star, this becomes equals to psi B mod square. Why? Because the position parameters are also same. You see, position parameters are x1, see x1, x1, x2, x2. That's why this becomes equals to mod square. Understood? Okay. So now move towards next. You have to multiply this with this. So psi A x1 multiplies by psi B star x1. Okay, psi ax1 psi bx2, psi ax1 psi bx2 multiplied by this psi b star x1 psi a star x2, psi b star x1 psi a star x2. Similarly, this multiplies by this and this multiplies by this. This psi b x1 multiplies by psi b star x1 becomes equals to psi b mod square, and this multiplies by this equals to psi a x2 mod square. Now you have to use integration on all these parameters. Apply integration on this, on this, on this, on this, on this, on this, and similarly on this. Understood? Okay. Also, for single integration, you have to use single parameter. See here, you are taking x1, so integrate our x1. If you applying integration on this x2, so you will only integrate our x2. Now if you apply integration on this is x1 and x2, you will not use this both in simple integration. You have to use same parameter. So this is x1 and this is x1, so you have to take this and this value in one integration. So psi a x1 psi b star x1, psi a x1 psi b star x1, and this our integrate our dx1. Similarly, this second parameter x2 and x2 comes on another single integration, psi b x2 psi a star x2, psi b x2 psi a star x2. Okay, similarly for whole procedure. So for the same wave functions and the same parameters like x1, these are orthonormal conditions which are equals to 1. There are only two orthonormal conditions, four orthonormal conditions. You see, psi a x1 multiplied by psi a x1, that's why psi a star x2. Okay, so this is equals to 1. This is also equals to 1, but this is orthogonal, not orthonormal. Why? Because psi a x1 multiplies by psi b x2. This is not the same. Opposite wave functions integration over minus infinity to positive infinity goes orthonormal condition. Orthogonal condition. That's why this is become equals to 0. This is also opposite 0, opposite 0, opposite 0. This is same. That's why 1. This is same. That's why 1. So 1 multiplies by 1 becomes equals to 1, and 1 multiplies by 1 equals to 1, and there is a plus sign. So 1 plus 1 2 under 2 mod square a, and mod a square becomes equals to 1 by 2. Okay, so now you have to take the square root, so a becomes equals to 1 by under root 2. But if you have to write general condition, so the general condition is you have to take a is equals to 1 by under root n factorial. So if there are 2 particles, so n must be equals to 2. If there are 3 particles, so n must be equals to 3 factorial. 3 factorial means 1 by under root 6. These are 2 problems. Now move towards the next third problem. So this is our third problem. What it says, wave function of, so it says that there is an infinite potential well where there are 2 particles. The one is psi x1 and the other is psi x2. Okay, you have to find their wave function. Like these both particles are if distinguishable. If both these particles are distinguishable, the next step is what if the both particles are indistinguishable. This is particle A, so psi, the wave function associated with this particle is psi x1 and this psi x2. So as we know that the general wave function of a single particle is equals to under root 2 by a sine of n pi x by a, and the energy associated with the particle is En equals to n square h cut square pi square by 2 m a square. A is the position, length you can say. So if these 2 particles are distinguishable, then you know how you can write the expression for distinguishable. Like if the particle is in position x1 and the other is in x2, so psi of x1 x2 becomes equals to psi n1 x1 for first particle and psi n2 x2. So this is the value of psi. You just have to multiply twice, but the only difference is that for first particle there is n1, for second particle there is n2, and the position for first particle is x1 and the position for second particle is x2. So it becomes equals to psi x1, this is equals to under 2 by a sine of, now n pi x by a becomes equals to n1 pi x1 by a for first particle, and similarly for second particle the amplitude is same, sine of n2 pi x2 by a. This multiplies by this becomes equals to 2 by a, and sine of this expression multiplies by sine of this expression. So this is the wave function of 2 distinguishable particles, and the energy associated of that distinguishable particles is equals to, if you are finding total energy, so you have to sum both particles energy. So the energy for particle 1 n1 and energy for particle n2. The only difference is that for particle 1 n becomes n1, for particle 2 n becomes n2. All other parameters became the same because these are constants. So n1 square plus n2 square came out because these are different for both particles. We will take common this, so this is the total energy if you have to find. So now what if these 2 particles are indistinguishable? if these two particles are indistinguishable, so what let there are two things that the particles are indistinguishable. Either if it is bosons, or hope so it is fermions. So let us first calculate if these both particles are bosons. Okay, so for the case of bosons, you know, if two particles psi x1 and x2, this is becomes, because these are two particle system as we did earlier. Like for two particle system, you have to use the value of a, which is equals to 1 divided by under root n factorial. N is the number of particles. If there are two particles, so 2 factorial. 2 factorial becomes equals to 2. So this is the value of a, means normalized constant. You can say amplitude of your wave function. So this is the value of a. But for the case of bosons, you can write your wave function as psi of n1 x1 psi of n2 x2. For particle A, for particle B, you can say for particle first n1, for particle second n2. Again, psi of n2 x1 psi of n1 x2. This is the wave function of two particles in case of bosons. Now you just have to put the value of that wave function, which you already find above. Psi n1 x1 becomes equals to 2 by a. So you can see here under root 2 by a, here is also under root 2 by a. When 2 under root 2 by a multiplies, you will get 2 by a. That's why I get off 2 by a. Okay, and here sine of, because n1 x1, so sine of n1 pi x1 by a. For this sine of, because n2 x2, so sine of n2 pi x2 by a. Understood? That's all. Now plus plus, you know, in case of bosons there is a plus sign at the middle. Okay, now psi n2 x1. So again there are two psi, both have under root 2 by a, under root 2 by a, both multiplies, you will get 2 by a. Again I get 2 by a beside. Okay, so n2 x1, so sine of n2 by x1, because x1 by a. For psi n1 x2, sine of n1 pi, because x2, so x2 by a. This multiple. So this is the value of your two particles if are identical bosons. Their wave function can be written as this. Okay, 1 by under root 2 multiplied by 2 by a becomes equals to 2 by under root 2 a, and 2 by under root 2a becomes equals to under root 2 by a. Okay, so that's all. Now the next possibility is that if your two particles are identical fermions, what you have to do, the only thing, there is a minus sign now. In case of boson there is a plus sign, but in case of fermion there is a minus sign. The amplitude is same because there is two particles, so 1 divided by n factorial, n equals to 2 because two particles, so 1 by 2 under root 2. These are same which we did here. Okay, and amplitude is also same. The only difference is now there is a minus sign. Okay, so that's all for problem number 3. Now let's move towards the problem number 4. Problem number 4, write down the Hamiltonian for two identical non-interacting particles in infinite square well. Now there is an infinite square well, so you know that the particles are now indistinguishable. Okay, verify the energy of fermions is in first excited state is equals to this. You have to find the energy of fermions in the first excited state must be equal to this. You have to prove this energy, okay, by the condition that you first have to write the Hamiltonian for two identical non-interacting particles in infinite square well. Infinite square well, so these are indistinguishable particles. We also know fermions are indistinguishable particles. Okay, and you have to prove that fermions is in the first excited state, and E must be equals to 5 pi square h cut square by 2 ma square, because there are two particles. So now let's take there are two particles, okay, inside an infinite square well. So how you can write the Hamiltonian? So you can write the Hamiltonian for one particle is minus h cut square by 2m partial square divided by partial x1 square for first particle. If there are two particles, so again minus h cut square by 2m2 partial square divided by partial x2 square. This is for x1 square for first particle, x2 square for second particle. I am taking mass m1 and m2, but in question it says identical, means both particles are identical, means their masses must be same. So in next step I take mass as identical, means common for both particles. Okay, so this is the value of Hamiltonian for two particles. Okay, and you also know that the Schrödinger wave equation can be written as h psi equals to E psi. Okay, h psi equals to E psi. Now what you have to do now, putting the value of Hamiltonian in this Schrödinger equation, h psi becomes equals to E psi. Okay, now you have to take minus h cut square by 2m common and d square by dx1 square plus, if minus is common, so plus d square by dx2 square. This is the value of Hamiltonian. So here E of psi. Now because these are fermions and there are two particles and those are indistinguishable, so wave function can be written as a psi ax1 psi bx2 psi bx1 psi ax2, and there is a minus sign in between because these are fermions. And psi of a and psi of b, you already know that which we did in the first equation, that psi for first is under root 2 by a sine of this expression. Okay, so for first particle, because here is the conceptual thing is that you should have to take n1 equals to 1 and n2 equals to 2. Why? Because you know the properties of fermions, that fermions in fermions no two particles are stay in a single state. Okay, no two particles, there are two particles and these two particles not be in the same state in case of fermions, because fermions never stay in the same state. If more than two particles, they will only stay in a state alone. So if particle is in state 1, so the other particle must be in the excited state. So if you are taking the first particle in n1, so the other particle must be in n2. So here for first you will take n equals to 1, here there is n but I am taking n1. So for the second particle is b, second particle is b, first particle is a. Understood? Okay, keep in mind. So for second particle you have to take n equals to 2, so that's why 2, because position x2, so position x2 minus as it is. Now particle 2, so you have to take n2, and position is x1, so x1. Particle is first, so you have to take n1, so n1, so n2 becomes n1, and position is x2, so x2. So this is your expression of the four fermions. Now you need to take the value of these two. You have to need the values of d by dx first, then their double derivative d square by dx1. Then you need d by dx2, means derivative with respect to x2, and their double integration. So here is your wave function. Now you have to take this wave function first with respect to x1, then you have to take their double derivative, then the next step is you have to integrate this expression with respect to x2, and then you have to take the double derivative, then all of these value after finding you have to put in this expression, and after calculating you will get your answer. So let us calculate. So here you first have to take the derivative with respect to f1 x1 of that psi function. So This is as usual because two particle system. For two particle system, it a becomes equals to under root 2 by a, because 2 by a and 2 by a is common. 2 by a multiplies by the amplitude a, which is 1 by under root 2, and this becomes equals to under root 2 by a, as it is this what I am saying. Okay, 1 by under root 2, the value of a, and this common, and 2 by a multiplies by this expression, you will get under root 2 by a. Okay, so this is what 2 by a. So here you have to use product rule. Here you have to use product rule, and here you have to use product rule. Take this and derivative of this, then take this derivative of this, take this derivative of this, and take this and take derivative of this. Okay, so after calculating you will get your this answer. Okay, now again you have to take the double derivative. Again you have to use product rule here and here. Take derivative of this, remains constant. You may take derivative of this remains as same. Again as usual here. Okay, after calculating you will get your this answer for psi square d square psi by dx1 square. This is your final expression. Similarly, you have to take the derivative with respect to x2, then take the double derivation, you will get your this answer. Now you put the value of x1 double derivation and x2 derivation in your Hamiltonian here. So this becomes equals to minus h cut square by 2m. This is the same which I find under root 2 by a. Here is common, here is common, again comes out, so this comes out. Now you have to write your this expression plus this expression. So this expression plus this expression, you see this expression. Now you just have to manipulate that pi by a whole square, and here also pi by a whole square. Take common, okay, and multiply this and plus this plus this. So this is common, you see. So again this expression you write plus this expression you write. Again the next thing is 2 pi by a is common, whole square, 2 by a is whole square. Again 2 by pi by a, take whole square common, and this expression as it is. Now you can see this expression is basically the expression of psi, and this is also the expression of psi. So reduce this expression as psi and reduce this expression as psi. Okay, but the thing is that you just have to take this under root 2 by a comes inside this value, then this equals to psi, because inside there is an amplitude value which is 1 by under root 2 and 2 by a, which is basically under root 2 by a. So this under root 2 by a multiplies by this, then it is reduced to psi. This is wrong, but this is not here. Okay, now this is reduced inside psi. Only thing the left is minus h cut square by 2m. You just have to take minus pi square by a square minus 4 pi square by a square. Okay, and take psi common. This psi cancels with this psi, you will get minus h cut square by minus pi by a square minus 4 pi by a square, which is equals to minus 5 pi square by a square. Minus plus for 5 pi square h cut square by 2m a square. So this is the thing which we have to find. So that's all for this problem. Okay, next move towards our last problem, which is that construct the completely anti-symmetric wave function for three particles A, B and C for three identical fermions. Means these are indistinguishable particles, and now there are three particles XA, XB and XC. Understood? Of an infinite potential well, one state is in psi 5 and the one is in psi 7 and the one is in psi 13. You have to write the expression of the three particle wave function in case of fermions. If one particle is in psi 5, other is in psi 7, other is in psi 13, means n is here 5, n is here 7 and n is here 13. Okay, where x is here xa, because particle first is xa and second particle, so particle is b, so third particle we will take c. This is the only thing. This is one part. The second part is construct the completely symmetric wave function. Here anti-symmetric because fermions are anti-symmetric. But the second part, construct the wave function, completely symmetric wave function for again the similarly three particles, but now in case of bosons. Symmetric, symmetry is only in bosons. And there are three conditions more in part 2, that if all are in state 9, means all these three particles A, B, C are in state 9. Yes, they can stay in the same state because these are now bosons. But in fermions, these all three particles not stay in the same state because these are fermions. This is the property of fermions. They can that no two particles stay in the same state. Okay. But in case of bosons, now he is saying that all three particles is in state 9. Yes, this is okay, but he says we need the expression. Okay, we can write, no issue. The next B part is if two are in state 3 and one is in state 13. Yes, that is the possibility that two particles are in state 3 and one is in state 13. This is the possibility in case of bosons. And the last one is one is in state 5, one is in state 7 and one is in state 13. Yes, that is also the possibility. The same thing 5, 7, 13, but in case of fermions, now you have to write 5, 7, 13 in case of bosons. Okay, so let's start over this problem. So here we are starting our solution for three particles. For fermions, you have to just write the wave function. Okay, so because there are three particles, as you know, the amplitude must be equals to 1 by n factorial, and for three particles is 3, so 3 factorial becomes equals to 6. Now because there are three particles, so each particle have an amplitude under root 2 by a, so each has common, so you will take under root 2 by a and power 3. Now how you can write the three particle system in case of fermions? There are how many possibilities? First is just an easy thing is that first take a, b, c, then take their inverse in with negative sign because these are fermions. If you take a, b, c, because 5 first particle is 5, second is 7 and third is 13. I am taking first particle is a, in which is in state 5, and second 7 state is in b, third in c. So this is a, b, c minus c, b, a, minus c, b, a, you can say, plus now you will take b, c, a, b, c, a minus c, b, a, minus c, b, a. Now you will take c, a, b, c, a, b minus ACB, ACB. Okay, that's all for the three particle system in case of fermions. The next part is he's saying that all is in state 9, but now the case is bosons, because all is in state 9 because there are three things. So again you have to take their cube, and all is in state 9, so there is only one state, so the value of amplitude is 1 divided by 1 factorial, which is equals to 1, and all is in state 9, so here is the only possibility, state 9, state 9, state 9, all particles, so A, B, C. This is okay. So the B part is here, and that 2 are is in state 3 and 1 is in state 13. So the only possibility is that again this is the value of amplitude. Again there are three particles, so 2 by under root 2 by a whole cube. So 2 are in state 3 means 3a, 3b, 13c. The next possibility is 3, 13, 3, and the last possibility is 13, 3, 3. Understood? Okay. So last case that all three particles are in different state, that's one in psi 5, one is psi 7 and one in psi 13. Okay, so again the same thing which we did here, these are fermions, that why minus some minus sign, but here all plus sign, the same thing. So that's all for our problems of many particle system. So we will discuss some more problems in next lecture. Thanks for watching. Allah Hafiz.